Okay, today is what's called estimating finite sums. We are getting approximate values. We will eventually be using the calculus that we are kind of building our way up to get more exact answers. But this is where the foundation of that starts. And to even kind of break that down even more, we're going to take a little trip back to elementary school, because you probably could have done this problem back in elementary. If Jane travels for 20 miles an hour for 3 hours, how far has she gone? 60 miles. Yeah, don't overthink it, right? If we're going 20 miles an hour and I drive for 3 hours, I go 60 miles, right? Distance equals rate times time. Okay, and our rate was 20 miles per hour, and our time was 3 hours. And I want to show you something here. Think about the labels. If I've got an hour in the bottom and an hour in the top, don't those cancel? 20 times 3 is 60, and my label that's left is miles, right? Kind of the same idea is going to happen. Now we're going to look at it kind of bridging that way into calculus. What if I were to create a graph that had those two values on it? Our miles per hour, which would be the velocity, right? Miles per hour for 3 hours. If I were to create a picture of that going on with our velocity here, our miles per hour, and our hours here. Well, if our velocity is constant, it's just a horizontal line up at 20. And we're supposed to look at that over the first 3 hours would be this right here. Look at the shape it's creating for us, right? And if we were to look at the numbers on that shape, the rectangle, what of that shape would get us to 60? It's area, right? And so what we're finding is that the area formed by our velocity curve and the x-axis actually gives us the same thing as the distance traveled there, which was our base times our height, or our 3 hours times our 20 miles per hour. And again, those labels cancel, right? And we would get 60 miles. And so what you're seeing here is kind of the foundation for where we are headed with this, being able to find total distance traveled. If you remember first semester, I asked you that question several times. How far, what is the total distance this particle has traveled from 3 seconds to 7 seconds? And we had a way of attacking it. We would break it down by the zeros of the velocity and look at when was the particle moving left and when was the particle moving right and what was the displacement on those different intervals. Remember doing that? What we're seeing is a different way of doing it, and it's by our velocity. The velocity will do that for us as well, and it actually will kind of take care of the whole right and left thing. We'll see eventually in a couple days. But it becomes this big concept up here. The area under our velocity curve is equal to the total distance traveled. We just saw a velocity that was constant. Let's look at a velocity that is not constant. If we change her velocity to the function t plus 2, how far does she travel in 4 hours? We again can do this geometrically, and we'll be able to do this geometrically if we are looking at some sort of a linear or constant function. So if I were to then kind of attack it the same way that we just looked at, what I'm looking at, the function v of t, if I were to graph that, remember that's just a linear equation, y equals mx plus b, right? How I graph mx plus b. Start with your y-intercept, which in this case would be up at 2. And we've got a slope of 1, so we go over 1, up 1, right? And we're going to do that for the first 4 hours, so until we get up to 4 hours here, up 1, over 1. And that would be a picture of our velocity curve this time. And what we just learned is that the area under this curve, so connecting that to our x-axis, this area right here will be the same as the total distance traveled. But this is a little bit different than a rectangle. What shape are we now looking at? Triangle plus a rectangle. Anyone see a different shape? A trapezoid, okay? Now, does it matter if I look at it as a triangle and a rectangle or a trapezoid? Not at all, okay? You can break it down either way. You get the exact same area. Since we've already looked at a rectangle, let's go ahead and look at this as a trapezoid, trapezoid with your base. So our bases are the parallel lines in a trapezoid. Just a reminder, this would be one of your bases. This would be another one of your bases, and it doesn't matter what you call base 1 and base 2, but it's the two parallel lines. And when we talk about the height, and geometry is always misleading, the height is your distance between bases, right? So if I were to do this in terms of a trapezoid, our formula is 1/2 times the height times base 1 plus base 2. Our height, again, being the distance between our bases. Well, if one of my bases is here and one of them's here. The distance between those is 4, right? Okay. The length of one of these bases is pretty easy to see because it's just up at 2. So that has a length of 2. The other one might depend a little bit on how accurately I drew it. But remember, guys, if we want to know where this is, how high this dot is, that's just a dot on the curve at time equals 4. So I could just come up and plug it in here and see what v of 4 is, right? And that will tell me what the height on that base is, or what the length of that base is. V of 4 being 4 plus 2 or 6. All good so far? Okay, so I'm just finding the area of this trapezoid using my trapezoid formula. 1/2 times 4 would be 2. 2 times 8 would be 16. Label. What do you think? Miles. Yep. Miles per hour times hours leaves you with just miles. And again, if you don't remember the rectangle area formula, you absolutely can break it down into a rectangle and a triangle. Trapezoid formula. Okay, so works as well. You would also get 16. You just have to add the two parts together. Questions? What we've seen so far is a constant and a linear. There is one other option when it's linear. We saw the trapezoid. We saw the rectangle. The triangle would be if that first initial y-intercept was at 0. So the rectangle came from a constant velocity, right? A triangle would come if your velocity crossed through like at the origin, like that. You could get a triangle, 1/2 base times height, right? And then the trapezoid is the one we just looked at on the last page. Cross through maybe higher than that. And we saw that shape right there. But what if the velocity is not even a line at all? That's where then the calculus is going to come in a little bit more. That's really easy to do geometrically and maybe even faster to do geometrically. The next part is why calculus is used for this. What if it's not linear? We are going to use this thing that is called rectangular approximation method, abbreviated RAM. Okay? And what happens in the rectangular approximation method is that rectangles are drawn underneath the curve. And eventually, through our calculus, we're going to draw so many rectangles under there that it's going to be nearly equal the area. What you see up here is very basic ones where there's not a ton of rectangles drawn. And so it's not a great approximation yet. But we have it labeled there as LRAM, MRAM, and RRAM. Using your common sense, what do you think L, M, and R stand for? Left, middle, right. Yeah, left, and actually M is going to be midpoint. R is right. It's telling you what part of the base of the rectangle to use to create the height. Okay, which side of the rectangle am I using to create the height? In left RAM, the left side of the base, so if this is our base, the left side of it, which would, oops, this is left side of it, which would be right here, is the side we use. When it hits the curve, that becomes the height of our rectangle. Our RAM says, okay, if this one's my rectangle, the right-hand side of it, when the right-hand side of it hits the curve, that becomes the height of the rectangle. And MRAM stands for midpoint. So wherever the midpoint, if this is my rectangle, wherever the midpoint is, I follow that up, and when it hits my curve, that becomes the height of my rectangle. So it's telling us which part of that. Now, looking at this, it seems like, well, why would we use anything other than MRAM? Doesn't MRAM look like a way better approximation for the area under that curve than L or R? Guys, not all your curves are this shape. Okay, so sometimes MRAM is going to be the best. Sometimes with whatever curve it is, L or R will be better. And we won't use it a ton because eventually we're going to move on to something even more effective than this. But this is kind of the foundation for where we are headed. Okay, so let's talk about the basics of this. Draw 4 rectangles to represent the area under the curve. Use the endpoint. So a lot of times what they're going to do is tell you how many rectangles to do. So to start that, you're going to take whatever distance you're doing and equally split it into those 4 spaces, which I have drawn for us on there. So this represents the base of one of our rectangles, and it says RAM, which means use of this base, use the rightmost point, follow that up to your curve, and once you hit your curve, then you can complete the rectangle. Again, use of that base, use the rightmost point, follow that point up to the curve. Once you hit the curve, draw in the rest of your rectangle. Rightmost point, follow that up to the curve. When you hit the curve, complete your rectangle. And our last one. Okay, so that would be a picture of our RAM. And we can do the same thing for the other 2. So the next one asks us to do the exact same thing with LRAM. And again, as we do that, of the 2 options here for our base, you've got the left end and the right end. It says use the left end. So I'm going to use the left end. I follow it up to my curve. Once that end hits the curve, I draw to the other side and complete my rectangle. Then I do the next one. So here's my next base. Use the left side of it. Follow it up to my curve. When I hit the curve, I draw in my base. I know your guys' pencils obviously can't move like mine can on the board, but if I were to draw the base, another way of looking at this is if I were to take that base and just trace it up to my curve, when the left-hand side of that line hits the curve, I stop and I draw in my rectangle. I'm going to do that one more time here, and again, I'm going to use the left side because it says LRAM. Trace that up. Once it hits my curve, I finish out drawing my rectangle. And then our last one, MRAM, again using our midpoint. So of my base, which would be right here, the midpoint would be approximately here, and I follow that line up to my curve. When it hits my curve, then that's where I'm going to draw the base there. Okay, or I could do like I was doing earlier, draw in the base and just trace it up to. When the middle of that line hits my curve, I finish out the rest of that rectangle. Here's my midpoint. Follow that up to the curve. Draw in my base. Now, transition this to like actually finding the area. Then they're rectangles. The area of a rectangle is base times height. So now that I've drawn that, we use that particular value. So if I go maybe back to here, if I wanted the area of this individual rectangle, I would take whatever this length is times this height right here, add it to the next one, whatever length this is, times this height right here, and so on until I've added up all of our rectangles. Okay, so let's go ahead and do that with this problem right here. It says graph the region defined by f of x equals 4x minus x squared and the x-axis from 0 to 4. So they're asking us to graph that, and we're finding the area under that curve, between that curve and the x-axis. So if I were to draw that, which is the first part of that question. Okay. Because it asked me for 4 partitions here on the next one, it says 4 subintervals, 4 partitions. I'm going to use the actual points at 0, 1, 2, 3, 4. So at 0, if I were to plug 0 in here, 0 minus 0 is 0, so it'd be a point 0, 0. Plug 1 in there. 4 times 1 minus 1 squared, 3. Plug 2 in there. 2 times 4 is 8, minus 2 squared would be 4. Plug 3 in there. 3 times 4 is 12, minus 9 is 3. And 4 times 4 is 16, minus 4 squared is 0. So we're looking at this curve right here. That was the first part. Graph the region defined by that and the x-axis from 0 to 4. Part B, partition that into 4 subintervals and show the 4 rectangles that RAM uses to approximate the area of R. So if I were to partition this into 4, there'd be 1, 2, 3, 4. There's my 4 bases. And I'm supposed to draw in the 4 rectangles using R. So of 0 and 1, I would use 1 because that's the right side of it. Follow 1 up to my curve and draw in the rectangle. Use 2, follow that up to my curve, draw in the rectangle. 3, follow that up to my curve. And then this one's a little bit weird. What does the rectangle look like at 4? It looks like nothing because the height at 4 is 0. So you don't have a rectangle on that rightmost end, and that's okay. Use that to approximate the area. I just find the area of each of those rectangles. So base times height. And again, I'll stress, guys, the height comes from the function itself, right? The height is when I plug 1, for this particular one, into the function. Where did it end up right here? It ended up at 3. That's the height of that rectangle. So it'd be 1 times 3. Base times height of the next one would be 1. The distance from 1 to 2 is 1. Height is the rightmost side, so when I plug 2 into the function, which is up at 4. From 2 to 3 would be a distance of 1 again for the base. Height at 3 was 3. And yes, the last one had a base of 1, but a height of 0. So I'm going to show it, but it doesn't add anything to our total there. And as I add all of those up, 3 plus 4 plus 3, we get 10. Now, a lot of the times, especially if we're the ones creating this, those bases are all going to be the same length. They do not have to be, and we'll run into problems where they vary the length of that base, and we'll have to be a little bit more cautious about how we do that. But a lot of times when we're equally dividing them, you'll see that same number happen over and over and over for the length of the base. Okay? Any questions so far? All right, now we get to use that program on our calculators. So, in order to do a program, you are going to need to go type that function into Y1. Jack, I don't think I put it on your calculator. All right. After we have typed the function into Y1, are we all ready? This is what you're going to hit. Go ahead and clear out of the Y equals, okay, and hit program, which is middle of your calculator, like 3rd or 4th button down right there. It says PRGM, program. And you're going to execute that program. So program, and we'll execute. It's called RAM. So if you do not have RAM right there. And it should say A equals question mark, right? A and B are going to be the ends of your interval. Here's A, here's B. So we type in 0, hit enter, type in 4. Oh, sorry, hit enter one more time. Did you type that function into Y1? Go to Y1 here. Oh, yeah, you do have it in there. Okay. There you go. Okay. And then it's going to ask you how many subintervals you want. Well, we're going to do 10 for the first one. So go ahead and hit 10. What it's doing is drawing 10 rectangles in there. We drew 4. It's drawing 10 of them in there. Now, your program is designed to give you all three, LRAM, MRAM, RRAM. So you got to make sure you pick the one, whichever one you were asked for. Or maybe you're asked for all three. Okay. You'll notice the higher the number, so I forget what that answer was. 10.56. So if you got 10.56, go ahead and move on to 50 subintervals and 100 subintervals and 500. And I want you to notice, do the numbers get closer together or farther apart? What's changing as we add more rectangles into there? And once you type in 500, it's probably going to take a minute to think on it. That's a lot of little rectangles for it to draw in there. But what you're going to notice, and I don't know, hopefully you're paying attention to the other numbers around it. Did you notice as we got more and more rectangles in there, the left and the right and the middle all got a lot closer to being the same approximation? Did you guys notice that as you were doing that? Okay. The more rectangles we draw, the more accurate, the closer it is to the actual area under there. We will not notice, let's see, 6, 6, 7. So it kind of looks like, I'm betting if I were to find the exact one, it would be 10 2/3, right? You see where this one is headed here as we get more and more rectangles under there. So, but that's what your program can do for you. We will not use this often, but if it were to be a whole bunch of rectangles equally spaced, we can use this program to find those for us. Any questions for me? Okay, so we've done this geometrically. We've done this with our estimate with RAM. We can also do this from a table of values. So kind of looking at the whole approximation by table of values. And this we're going to notice is kind of a little bit different. It is not a consistent function here. It says the table below shows the velocity of a model train for 10 seconds. Estimate the distance traveled by the engine using the 10 subintervals of length 1 using RRAM and LRAM. So if we were to look at this, one of the things you can do is just translate the data into a picture. And sometimes that's easier for us to visualize what's going on. If I wanted to do that, remember that what we're looking at are just ordered pairs, right? So if I were looking at this, this is the ordered pair 0, 0, 1, 12. It looks like we get up to like 22. Okay, so if I were to kind of draw an approximate picture of what's going on here, I would have a dot at, let's see, 0, 0, 1, 12, 2, 22, 3, 10, 4, 5, 5, 13, 6, 11, 7, 6, 8, 2, 9, 6, and 10, 10. So notice that this curve is definitely not consistent. As we look at that and finding the area underneath it, it asks us to do RRAM and LRAM. But I want us to see if we can go from drawing a picture and drawing in the rectangles and everything to understanding how I can then just look at the table and find that for myself. Now, each of our bases are going to be the exact same length. Let's do the RAM first. So here's my base that goes from 0 to 1. I would use 1 as my height, right? That's the rightmost. So if I'm doing RAM, my rectangle would be a 1 by 12 rectangle, right? Plus, and as I do the next one, it'd be a length of 1 by, my rightmost number would be over at 2, so up to 22, 1 by 22 rectangle. And a 1 by, use 3. Are all my bases 1? Yep. Okay, my next rectangle is going to use height of 5. If I'm using RAM in that table, am I using all of these values? All but, which one's never the right side of a rectangle? 0, the first one, right? The first one will never be the right side of a rectangle, will it? So, and if I'm multiplying all of them by 1, do I even really need the 1 in there? So can you just total up all the numbers except for the first one? Okay, so if I total all those up except for the first one, what do we get, first of all? Going to need a confirmation here. That's a lot of numbers to type in and easy to make a mistake. 97. Okay. Okay, so let's speed up this next one. It's going to ask us to do LRAM. Now, if in RRAM I did all the numbers except for the first one, in LRAM I'm going to use all the numbers except the last one because it will never be the left-hand side of a rectangle, right? Is that making sense? So you kind of understand what I'm talking about right there. You can kind of speed this up for yourself. The base is still going to be 1, and then I'm going to use all of those except for the last one. Because the last one will never be the left-hand side of a rectangle. Okay, what are we getting this time? Okay, before we move on, again, trying to speed up our process when dealing with a table of data. Now, guys, if you understand what I just said, perfect. You can speed this up and know which one to add or whatever. What if the base was like 5 instead of 1? What if it went 1, 5, 10, 50, or 0, 5, 10, 15, whatever? Do I have to do 5 times 12 plus 5 times 22 plus 5 times... Is there a faster way to do that? Factor out the GCF. Can't I just add up all those numbers and multiply by 5, right? After I've added up all those numbers. So you don't have to do every tiny little rectangle by itself if they have the same length base. You can just wait to total it all up and multiply by the base at the end. Okay? Now, the last thing is this. What if they ask us to do MRAM? MRAM. And this time it says 5 subintervals instead of 10. So we're not going... Let me get a different color here. I'm not going to 1. I'm making it into 5 subintervals. 1, 2, 3, 4, 5 subintervals, which means my base is how long each time? 2. 10 divided by 5 equal rectangles. So if my base is 2, different color here, my base is 2 and I'm using MRAM, what number am I actually using for the height? 1, right? The number in the middle of that base. My base goes from 0 to 2. 1 is the number in the middle of that. So I actually use 1 as the height of my rectangle there when I'm using MRAM. Now go to your table. I'm going to do this in the table instead of writing it all out. There's my length of 2, right? The base, or the height, will be the number in the middle because we're using MRAM. So my height would be 12. Base length of 2, height of 12. Next one, base length of 2 goes from 2 to 4, height of, what's that, 3, right? Height of 10. From 4 to 6, height of, what's that, 5. From 6 to 8, height at 7. And from 8 to 10, our height would be at 9. So that would be setting it up 5 equal subintervals using MRAM. Okay. And while somebody's getting that typed in for me, does anyone have any questions on anything up there? What is it? 94? Although the program's kind of nice and handy, we really won't use it much. Understanding what I just did today, though, is going to be very important, especially without a calculator. Okay, so let me know if you have any questions. Otherwise, your assignment today is out of the book. 1 through 6, you are doing that without a calculator, so you do not get to use your RAM program for 1 through 6.